Okay, so now I'm going to talk about Hamiltonian mechanics in terms of a structure which is related to symplectic structures called the Poisson structure, or Poisson brackets. Okay, so the definition is as follows. If you're given a symplectic vector space, let's say Z with a symplectic form omega and two functions, let's say f and g, which are scalar valued functions on this symplectic vector space. Okay, then the Poisson bracket of these two functions. Okay, so you take the Poisson bracket of these two functions, and you again get another scalar valued function. Of f and g is defined as the following. All right, so you have f and g, two scalar valued functions. You take its Poisson bracket, you get again another scalar valued function. You can evaluate this at some point z in this vector space, big Z. And this is defined to be the following. So you need some scalar valued function, right? So you have omega, which is, of course, the symplectic 2 form. And symplectic 2 forms act on vector fields, okay, two of them. So what you want to do is that you want to associate with f and g two vector fields. So one way to do this, of course, is to look at the Hamiltonian vector field generated by f and g viewed as Hamiltonians. So you'll have xf, right, and xg, right? These are vector fields, right? You want to evaluate them to give you a vector, so I evaluate them at the point z. That's quite natural. And then I sort of take these two vectors now, and then I apply the symplectic 2 form to that. That gives me a real number. So again, it's like this construction, if you will, gives you a way of defining what is called a Poisson bracket, okay? Where, again, xf is the Hamiltonian vector field. Associated with f. Okay. All right, so let's look at an example of such a Poisson bracket. In particular, it's natural to look at the Poisson bracket which is generated by the canonical symplectic 2 form. And the Poisson bracket generated by the canonical symplectic 2 form is, of course, what is called the canonical bracket. Okay. All right. So let's see what happens. So if Z is 2n dimensional, we have sort of canonical coordinates. Let's call them Q1 to Qn, P1 to Pn. All right, that's quite natural. And so the Poisson bracket of f and g, right, is equal to the symplectic form applied to xf and xg. All right, so I'm going to write this in my bilinear form notation. So this is xf transpose J matrix xg, and I know what xf and xg look like just from the form of Hamilton's sort of equations, Hamilton's canonical equations. So this looks like the f, the p sub I. I'm going to sort of assume that the I varies from 1 to n here, so I'm just going to write it a little bit more compactly. The f, the qi, right? So this is the Hamiltonian vector field so it's generated by F and then transposed, and I have the J matrix, and then there's a dg d pi minus dg d qi. Right, so so this is more or less again what this scalar value function looks like, and so I can simplify it a bit more. So that is equal to okay, so df dqi. So I'm just essentially just multiplying out what that quantity ends up becoming. So df, dqi, dg, dpi, and then there's this implicit summation over repeated indices with raised and lower indices, right? So this is again the Einstein summation convention. Okay, minus df, dpi, dg, dqi. Okay. All right, so that's one way to do this. If you want to write this in terms of gradients, it's like and the symplectic matrix, you can. So this looks like the gradient of f transpose the symplectic matrix, and then the gradient of g. Right. So this is this is really the canonical Poisson bracket. So this is f g. Okay, so both of these expressions are commonly seen. Okay. All right. So another object which is of interest. So this Poisson bracket takes two scalar value functions and gives you another scalar value function. There is also another sort of bracket which now takes vectors and then takes pairs of vectors and gives you another vector. Okay. So this is what is called the Jacobi-Lie bracket. Okay, so square brackets x and y of two vector fields. Let's say x and y, and it is defined by the condition that if you take some scalar value function f, you take its exterior derivative, right? This is a one form. So the one form can be paired with a vector. So the exterior derivative of a scalar value function paired with this bracket of two vector fields, right? So, you know, basically it's like you're looking for something which takes two vectors and it gives you another vector, okay, or vector field. So this gives a vector field and this gives you one form. You can pair it, you get a scalar valued object. Okay, so this has to satisfy the following property, that if you take df and you pair it with y, so that's now one of the vector fields. So again, this is a scalar valued quantity. I can take its exterior derivative to give me another one form, which then can be paired with the other vector field. Okay, so minus df dot x dot y. Okay. So you might ask what this thing is, right? So if you think about it, this df paired with y is essentially the directional vector field, the directional derivative of f along the vector field y. Okay, so more or less it's like the way to sort of think about this is that what you're doing here is that you're taking the directional derivative with respect to y of the scalar value function f. And then once you've done that, you take the directional derivative of that object with respect to x. And then you're sort of doing the reverse here. You take the directional derivative of f with respect to x, and then you take a directional derivative with respect to y. Okay, so it's more or less a commutator, if you will, of the directional derivatives. So that's one way to think about this. Okay, and you want this to be true for all real value functions. Okay, so you can re-express this in terms of what is called the Lie derivative notation. Okay, so in Lie derivative notation, right, where you have the property that the Lie derivative with respect to a vector field of a scalar value function f is just, again, df dzi, right, xi. Okay? So, all right, so if you, again, this is essentially the directional derivative of f. It's like in the direction x. So if you want to write this, then again, this is the Lie derivative of the scalar value function f in the direction of the Jacobi-Lie bracket of the vector fields x and y. So this thing, right, can be written as the Lie derivative with respect to the vector field x and y of the scalar value function f. And then this left-hand side is the Lie derivative of f in the direction y, right? So Lie derivative of f in the direction y. And then on the outside, let me just write that more clearly. And then once you have that, that's a scalar value function. I can take the Lie derivative of that object in the direction x. So Lie derivative in the x direction. And then the other one is just the sort of the permutation of it, right? So Lie derivative with respect to y, Lie derivative with respect to x of f. Okay, so I can actually remove this parentheses. All right, so again, more or less what you're saying here is that this thing is morally the commutator, if you will, of these things. And in fact, it should be mentioned that, so we talked about thinking of vectors as being related to this equivalence class of curves. Another way of thinking about vectors is by relating it to directional derivatives. Okay, and one nice consequence of thinking of it that way is that then that allows you to think of a vector field as an operator acting on something, and in particular, it allows you to think of, you know, the commutator of those operators, which is basically what this is. Okay. All right, so let's just write this now in coordinates and in vector notation. Okay. So in coordinates, what you get is that the components of this Lie derivative of vectors, right? So this is again a vector field. So the Lie derivative of two vector fields is again a vector field. So I'm looking at the j component of it is equal to xi d d zi yj, okay, minus yi d d ci xj. Okay, and then again there is this implicit summation over the repeated index, which is I here, via the Einstein summation convention. Okay, and then and that sort of makes sense. You've sort of summed out over the I, so there's no longer dependence on I, and there's only dependence on j, which is exactly what you have on the left-hand side. Okay, and then in vector notation, then what you have is that the bracket of these, the Jacobi-Lie bracket of these two vector fields is equal to, it's x dot the nabla operator acting on y minus y dot the nabla operator acting on x. Okay, so those are sort of, again, two ways of thinking about the Jacobi-Lie bracket, and perhaps in a more explicit way. And one final thing is to relate the Jacobi-Lie bracket to the Poisson bracket. Okay, so there's a proposition which I won't prove, but I'll just state. The Jacobi-Lie bracket and Poisson bracket. Satisfy the following, that the Hamiltonian vector field of the Poisson bracket of two scalar valued functions, okay, that makes sense, right? The Poisson bracket of two scalar valued functions is again a scalar valued function. You can look at the associated Hamiltonian vector field by thinking of this scalar valued function as a Hamiltonian. That's equal to, okay, so you have these two Hamiltonians, if you will, right? So if you want to relate it to the Jacobi-Lie bracket acts on vector fields. So the natural thing you might expect it to act on is the Hamiltonian vector field associated with each of these scalar value functions. Okay, so that's xf and xg. Okay, and then of course you can take the bracket, the Jacobi-Lie bracket of those two vector fields, those two Hamiltonian vector fields. And the claim is that that's related to this Hamiltonian vector field associated with the Poisson bracket of those two scalar value functions, but with a minus sign. Okay, so that's just an interesting observation, if you will. Okay, so so the next thing we're going to do is we're going to sort of think about first integrals in the context of Hamiltonian systems, and then express them in terms of Poisson brackets. Okay, so let's stop for now.